some stuff left from yesterday. I have stuff left from yesterday, which is this stuff. So I'll tell you a few words also because Radu mentioned it. But before that, let me tell you a joke from our friend Valery Slastikov. He used to tell us Radu and Luke. It goes like this. So it's dark, right? In the night, and there is this guy, and there is a phone with a light on top, and there is this guy that goes around it in some sort of random motion, obviously kind of drunk. And then a policeman approaches him and asks, "So, are you okay, sir? Can we help you? Can I help you?" And the guy said, I lost my keys. I'm looking for them." And the policeman, "Okay, let me help you." So, after half an hour of looking, the policeman asked, "Are you sure you lost them here?" "Somewhere there, but the light is here." Yeah. So to some extent, it describes the story of point defects in the sense that these are the things that we understand. That's where the light is. But there are a lot of interesting things out there in the dark. Beyond this very beautiful symmetry, that helps us understand things. So it's quite a challenge to understand, even numerically, to understand what goes beyond these very symmetrical point defects. Right. So that's an interesting area to explore. But let me tell you so far what we understand about these symmetrical solutions. And as you'll see in a moment, there are many ways in which you can go around the pole. So there are many radially symmetric solutions. Yeah. So what I wanted to present at the end of yesterday's lecture is something like this. In principle, you can the system whose qualitative properties we are interested in is a semilinear elliptic system of essentially 5 coupled PDEs, right? And sometimes it's convenient and of course it's easier if you can reduce it to something simpler, right? So you can take an ansatz like this, where you are on a ball in 2D. So when Radu was mentioning 2D and 3D, he was referring to the domain, and in general, and you can write this in polar coordinates, and then you can look for a solution of this form, where you have that u is a function depending on just the radial component, and so is b. And then you have some matrices, as in here. This is constant. E3 is just the vector 0, 0, 1. So this is the constant matrix, and then this is a matrix that varies when the polar angle varies, phi varies. So it's something like this. So if you make such a guess and you plug it in your system of 5, into your matrix system, if you are lucky, you'll get an equation just for these u and b. And moreover, these are ODEs. So it is a dramatic reduction in complexity, right? Instead of having 5 PDEs, you have 2 ODEs. So of course, it's very convenient. It's a very special solution, on the other hand, and you have to have a systematic way of producing such ansatzes, right? And then you ask yourself, okay, so this special solution, how relevant and important is it, right? So that's what I'll tell you in a more systematic way. But this is just an example in which you have such a reduction, And overall, this is still a coupled system of ODEs, And if you take b equal to 0, it becomes a bit less coupled, It becomes more like Ginzburg-Landau, which we know and love. If you add b, then the situation is a bit messier, And then there is somewhere here kind of a lonely potential here with k. that index that Radu was mentioning. And just to clarify, index is something that physicists use. So that's why you have index 1/2 degree, but yeah, degree should be really an integer. Mathematical point of view should be just okay. It's not like this. No, it's working. Okay, and then being a system of ODEs, it's needed one from qualitative point of view, and indeed, as Radu was saying, you have a sharp distinction between the case when it's P4 is greater than P squared and it's strictly less. But in most cases, you have that U and V are nice in the sense of having a definite sign, so either positive or negative, and also they are monotone. And that has to do with a maximum principle and the cooperative or non-cooperative system. And in the limit case, when you have equality, this should have been before here. V is a constant, and then you have just one ODE. Okay. And now this question that Radu was mentioning, stability. Yeah. First of all, what do you mean by stability? It's something like this. You look at this is Y is your spectral solution, and then you add arbitrary perturbation P, yeah, which are compactly supported with values into the set of all Q-tensors. Yeah. And then you look at such perturbations, and you want to see that this Y is a local minimizer for the energy, right? So any such perturbation should be greater or equal than 0. Yeah. So this is really what you mean by stability, that the second variation defined as in here is greater or equal than 0. Yeah. And this should be for any P like this. Yeah. And this is where we start seeing a bit the complexity. Because Y in principle depends just on 2 components, but P depends on 5 components. Yeah. So you start seeing the geometry of the Q-tensor when you look at this problem. Yeah. Stability is important also from a physical point of view, because physically you are only going to see those solutions that are stable, because otherwise the unstable ones will be wiped out by various thermal perturbations, say. Yeah. And also numerically, these are the solutions that are most commonly found through gradient descent schemes. The other types of solutions, saddle points and critical points, which are not stable, much harder to find. Yeah. So that's why this is an important issue, and it also helps us understand the geometry of this rather large dimensional set of Q-tensors, yeah, through its interaction with our Y, which, as you saw, is actually made of 2 components, and which you can understand very nice, very well. Yeah. Okay, so then we have some stability, and I'm going to skip over this, and then it's the dark side that I was mentioning. If you go beyond the stability, very little, beyond radial solution, you get symmetry breaking, and you have things like this. This is one of the few situations we can, well, at least rarely seen. There is no analysis of such things in 2D. There is interesting work in 3D, yeah, that you'll see next week. Of Pisante and Di Pasquale, and different line Young Yu, and phi. Okay, so let me go back to what I plan to present for today actually. So, right? So this is the energy that we are looking, we want to study, omega in the 2D domain. And here you can put epsilon to be in line with the Ginzburg-Landau paradigm. And you are interested in studying such a thing when epsilon is small. Yeah. And it turns out that it is sufficient to look just at the case when omega is a disk and to look at these kind of boundary conditions. Yeah. What do I mean by it is sufficient? I mean that these are the kind of defects, the point defects that are observed numerically and in experiments. Yeah. And in fact, you have a theorem, for instance, in 3D that if you have an arbitrary domain, omega, and you try to minimize gradient of n squared, yeah, where n is unit vector, then there will be just point defects, and those will look like x over mod x. Yeah, that's just in 3D. So there is a sort of universal behavior of defects, yeah, which allows you to reduce to this kind of say special domains and special boundary conditions. Yeah. And in here there is this k over 2, yeah, that we saw, and there will be quite a difference in whether k is even or odd. And the major difference that you can see immediately is that when k is even, this is a 2 pi periodic function, so it's a periodic function. Yeah. And when k is odd, it's not. Yeah. So when k is odd, you start with something like this, and after 2 pi, you end up with something like this. Yeah, in the opposite direction. So this is a line. Yeah, this will be described as a line. If you put it in this form, it will become continuous for k say 1. Yeah, on 0 to pi. If k is if k is odd, it will become, well, if k is even or odd, this will become continuous. But this will only be continuous if k is even. Okay, and corresponding to this, there is a topological difference on whether you have even or odd k, because in the case when k is odd, right? So you have line field perspective, you will have a topological abstraction for extending these boundary conditions continuously inside. Yeah, you can do it with vector fields if k is even, but escaping into the third dimension, as Radu was saying. But you cannot do it when k is odd. Okay, so that. Okay, so these are how the profiles look like. Yeah, so these are the index 1/2 defect. These are the one that we describe in terms of line fields, and these are the index 1, yeah, or -1 that can be described in terms of vector fields as well, right? So you can put arrows in a consistent manner on all these lines. And then there are the corresponding Q-tensor versions of those images, which is really what we are studying. Yeah, as I was saying yesterday, the way of getting from these to the other ones is just to flatten these parallelepipeds to their longest axis. Okay. And there will be fewer nice pictures today, I'm sorry. Okay, so again, this is the energy that we are trying to minimize. BR in R2 is a radius R between 0 going up to infinity. Q is in H1, and S0 is just the set of Q-tensors. Yeah, and this is the bulk energy density, where I put here squares just to keep track of the size of these coefficients. Okay. And now you have these well, strength k over 2 or index k over 2 degree, but that's figures as so, or Wilding number, which is more complex analysis terminology. And you put this kind of S plus. Why do you put this S plus? Because this will, if you put S plus like this and unit vector, these will be on the minimum of the bulk potential. Yeah. So this is precisely the constant that ensures you that these kind of matrices are in the minimum of this. Okay. And then you want to understand what are the symmetry properties of these. Yeah. So how many ways you can go radially, say, how many types of radial solutions you have for this kind of system. Yeah, and radial will mean many things because we are working with matrices, so there are many things, many types of symmetries, and in dealing with symmetries, it's useful to extend. I mean, so these are the boundary conditions essentially that we are using, but written in a matrix form. Yeah. So then we will proceed with a trick similar to the one that Valeria was using yesterday, namely a basis that changes as you change your data. Yeah. And it is adapted to the geometry both of the domain and of the target. Yeah. So this is to say that we also construct an MK perpendicular on this one, but this also depends on the polar coordinate. Yeah. And then you have the E1, E2, E3, which are honest constant vectors. Yeah. E1 is 0, 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. Yeah. And then you construct bases like this. 5-dimensional, so it should be 0, E1, E2. And I'm going to add E3 and E4, different ones, depending on whether I'm working with even or odd K, because as I mentioned, there will be quite a few differences. And while, I mean, what is the meaning of these? Well, they are Q-tensors, yeah. They are unit norm in this Frobenius norm, just that the scalar product on the space of matrices. So this is the scalar product. Yeah. Yeah. And so this is just an orthonormal basis. But the important thing is that you change. It's not constant. Yeah. It changes as you go around. And that really makes a huge difference, the fact that you have this adapted basis. Because if you write things in this adapted basis, the symmetries will amount to nice properties for these WIs. Yeah. In principle, WIs are functions of R and theta. However, the symmetries that we'll be choosing are such that they imply that WIs are really just functions of R. So things really simplify in this in a moment. Yeah. Okay, so this is a monstrous looking symmetry that is written here, which we call k-fold SO2 symmetry. So let me try to tell you a bit more of this. So you have X in R2, yeah. And then you have this thing that in this part is just a rotation. So you are rotating X from here, here. Yeah, so just a rotation by an angle k over 2 pi. And then you write this as a 3x3 matrix, so you add this one component, but then you want to rotate a two-dimensional vector, so that has difficulties interacting with this unless you make it three-dimensional. So that's why we add x0, yeah, and then x0 rotated. So this is just to say that x, which is two-dimensional object, is rotated by angle psi, yeah. So and this other thing tells you, if I'm making, I have something like this, yeah. this is the X, and this is the Q. And when I'm rotating this, I want to rotate this, keeping the same angle, essentially. Yeah. If you imagine Q as being, say, sort of unit vector. Yeah. So this is the kind of radial symmetry that is in there for one thing, and that is adapted to this system. And allows this dimension reduction, yeah, to fewer components. And then you can have some other types of symmetries. This was an SO2 spectral orthogonal group. You can consider the full orthogonal group, which means that you need to add the reflections, yeah. So then you have this monstrous looking symmetry that is pretty much as before. You can take here, but it has this L in addition. Yeah. So if you take alpha, which is the number, can be 0 and 1. If you take alpha equal to 0, you get precisely that symmetry that was before. If you take alpha is equal to 1, you also have this thing, which is precisely a way of writing the matrix that is diagonal with components 1, -1, and 1. Yeah. So this is reflection with respect to the vector on respect to the plane. Well, that's it, with respect to this E2 direction. Okay, and then you finally have this just up and down symmetry. Again, here you have reflection. Yeah. And this Z2 symmetry is independent of these two. So you can have one of these and have this one or not. Yeah.
Quick question. I lost track. What's P2 again?
P2 is the projection on the, yeah, because so X is two-dimensional. I add one variable, I make it three-dimensional. I rotate it. Yeah. I mean, I rotate just really these two first two components, and I'm left with a third component, which is 0. And I want to project it back to 2 dimensions. So it's kind of convoluted just because of this. Yeah. Yeah, so this is the projection on the first of a 3-dimensional vector to a 2-dimensional vector by cutting the third component. That's it. Okay. Okay, so why are these useful? Because, as I was saying, if you have these kind of symmetries, you have one thing in common: the decomposition into a basis that uses these has into a basis of this type. In here, instead of having X depending on R and P, just depends on R. Right, so your PDEs will turn into ODs. Yeah. So then you also have a reduction in the number of components. Yeah, and you can see quite dramatic differences. K-fold SO2 symmetry will have all the components here. Yeah, so all 5 components, but only 3 components here for K odd. Yeah, and if you have this additional reflection, you have just 3 components in the even case and just 2 components in the odd case. Well, Z2 symmetry again produces a reduction in the number of components, and then you can combine SO2 with Z2 or O2 with Z2. Yeah, and again you have some, way of expressing this in terms of these WI variables. Yeah, and the good thing about this is that it turns this system of PDEs into a system of ODs. Yeah, still these are fully coupled because pretty much every component will talk to every other component. Almost, there are still some nice cases that again can be detected using this the symmetry arguments. And okay, so what can we say? If you have this k-fold SO2 symmetry and also the Z2 symmetry solutions of the Euler-Lagrange equations, then you can you actually have something a bit better. You have k-fold Z2 as before, but you have this O2 symmetry. Yeah. So in principle, you are looking for just a solution of this type, and then you see that it actually has to be of this type. Yeah. So you are losing, I mean, the sum of the components will become 0. And then there is another theorem, later theorem, that looks almost like the previous one, but it's a bit different, and it's quite different, quite harder, yeah. Because for one thing, this is just about odd case, yeah. And then you are looking at the set of SO2, but not Z2 symmetric solutions, which means that more components will be alive, yeah. And then you see that the minimizers satisfy this more general symmetry, the O2 symmetry. And you have fairly, in some sense, non-uniqueness phenomena, because if you just change the sign of W3 to minus W3, you also get the same energy. Yeah. So that's providing you already a statement of non-uniqueness.
Question, Arghir. So you're referring to the Euler-Lagrange equations, the dynamical system, the ODE, they have their own Lagrangian?
No, it's a stationary thing. Everything is here. Everything is stationary.
No, but the ODE system, do you have the associated energetic representation?
Yes.
So these are the Euler-Lagrange equations of a associated. Yes. Okay.
Yeah. I mean, yeah, you can put a gradient flow to, and then do some gradient descent if you want to study things numerically. Yeah. There is an interesting landscape and so on, but we didn't get into that. Okay, so these are these k-symmetric solutions, and now what can you do in studying the stability? Yeah. Now, the easy case is this: when b is equal to 0, then your minimization problem becomes something like this. Yeah. So this is, pretty much like Ginzburg-Landau. In Ginzburg-Landau, it was 1 minus u squared. Then the difference is that here, this is actually a 4-dimensional, and this is a 5-dimensional thing. So the minimizer for this will be living on a 4-dimensional sphere. Yeah, and then you can look at the corresponding problem for the components. Yeah, so this will be just essentially a 1-dimensional coupled system. Yeah. And then what you get is a unique minimizer for any radius. Yeah, which is quite difficult to get in general, as you saw from Radu Ignat. But here it was quite cheap because it has a special structure. There isn't much coupling in the absence of that B. Yeah. So let me tell you a bit how it works. You compare the minimizer with a perturbator. Yeah. And then you have two parts. One is the second variation, yeah, which is something like this. The second variation is quadratic in P. And then you have some other term which is positive. Yeah. So if you want to show that this is positive, you just need to show that, well, non-negative. You need to show that the second variation is non-negative. Yeah. And this is just pure luck in a sense because the system was simple enough. Now, the second variation is non-negative. Yeah. This is something that is supposed to be non-negative for any P. Yeah. So whatever P you put here, compactly supported, this should be greater or equal than 0. I mean, this part is easy because it's obviously positive. But this part, I mean, it's a bit of a mess because it depends on this Q, which is the solution of a PD and OD, if you wish. In our case, it is an OD. But it's a function that changes when R changes. Yeah. So in principle, it's not clear how these two interact. Yeah. And this is the beauty of this Hardy trick that, or Icone, if you wish, that Radu was presenting. Namely, you use the fact that the U that here, I'm sorry, the W0 that component that appears there has a sign, yeah, and then you write your arbitrary perturbation as that special component times an arbitrary function, yeah. So instead of P arbitrary, I use U arbitrary, but I also use this W0 that is hidden in this Q, yeah, and then I use the equation. That equation gives me a way of combining gradients of W prime that appear here with the W without derivative that appear here. Yeah. So this is really, if you just plug in this substitution and you write what you have and you use this equation. This is in some sense the most obvious form, because this is minus a squared plus c squared. The norm of q squared is precisely that term that was mysterious here. Yeah, but this term appears here in the right hand side of the equation. Yeah, so if I multiply by this u general perturbation, this gives me a way of relating such a thing with gradients. Yeah. So really, this is this amazing trick that, after using the equation for W, reduces the whole second variation to something which is manifestly positive. Yeah, and then you can show that it's actually coercive. Yeah. So then you get this pretty much for free if you know this very nice trick. Yeah. Okay. So, now it gets trickier when you have B non-zero, because in the case when B is non-zero, you have a more coupled system. Yeah, and then we have that, as Radu was saying, that when R is small enough, you can use this convexity of the energy functional, which is really due to the fact that this controls the L2 norm with a constant that is the E, the first eigenvalue. Yeah. So the smaller R, the larger this constant. Yeah. So this is providing you a better and better control as R is small. Yeah. So then it will be able to beat this nonlinearity, and overall this will be a convex. But the more interesting case is what happens when R is large, and in fact you can show that you can make this negative. Yeah, so you have an instability phenomenon. Namely, you can if you have this symmetric critical point with just two components, you can construct a perturbation to make this second variation negative. And in order to do this, you don't actually need to understand the whole the whole shape of this y, this special solution, but that's what happens at infinity. Yeah. And again, at infinity, you have better information because you can do some linearizations and like that. But things are harder if you want to prove stability. Yeah, because to prove instability, you have just to provide a P that things are negative. But to prove stability, you have to show that for every P, things are greater or equal than zero. Yeah. Now, for one thing, this won't work for any K, just for the index of for the lowest index. Yeah, this is just like in Ginzburg-Landau. The the defects of lowest index will be the stable ones, because if you have higher index, you can split into two defects of lower index and then reduce the energy. Yeah. A similar kind of heuristic holds here as well. Okay. So if you take these two components to be a minimizer of this reduced energy functional, and here it should have been W0 and W1, not U and B. Then you see that the solution that is made up of these two components, the matrix solution made up of these two components is stable. Yeah, for all representation, for all B which are just in H10. And then, well, things get more complicated and more interesting. So this is something old, how you see things. So the important thing here is that we were able to do it for A up to 0. And A close to 0 is the most physical regime, and it's also the hardest from a mathematical point of view, because you see most couplings there. And A gets larger, you get more towards that simple case when Ginzburg-Landau, okay, so what we are able to show is that for A large enough, so there is some R naught depending on A, B, and C, so that if you go past that radius, there exist exactly two global minimizers, which are actually capable of O2 symmetry, not more than that. And well, they look like this, and in fact, one of the components is positive, and can construct a negative one as well, as mentioned before. And well, let's just a bit how it fits into the big picture. When you have, I mean, there is this dichotomy that Radu was mentioning. You can fix R and play with this epsilon, or you can. So the case when R is large and the constant epsilon is fixed is equivalent when with the case when you fix the radius, but you play with this constant. It just change of variables. If you write this energy functional balls of radius R, and then you want to rescale it on balls of radius 1, you get this constant here. So the case when R is large or epsilon is small is the same thing expressed in different ways. So you can fix the ball to the unit side, and then you look at what happens when epsilon is small, and that corresponds to the case when you fix epsilon and let R large, as was stated in the theorem. And well, in some sense, this is a bit more intuitive. You kind of see what happens when epsilon becomes small. Namely, you approach the minimum of this bulk potential. And if you are in an even K, the minimizer that you'll approach through, say, gamma convergence minimizer will be something of this form. So it will be, especially the answer will be modular topological issues. So, but in here there is no. There will be minimizer of Biot infra, harmonic map. And the important thing in this kind of argument will be that the minimizer is smooth. So this is really just about understanding the connection with the limit in a very sophisticated way. So I'll talk more about this next week. Those will be around. But let me just mention these energy scalings that differentiate between an even and odd degree. Namely, for even degree, given that the limit problem is smooth. There is no topological obstruction, yeah, to extending the boundary conditions continuously inside, because you can escape in the third direction. You have that the energy is bounded. But for odd K, there is a topological obstruction, like in Ginzburg-Landau. So you also have, like in Ginzburg-Landau, no gaps in on level of energy. Yeah. So this is at an energetic level, the fundamental difference between the even and odd case. Yeah. So let me show you just briefly that there is a whole group of things that can happen. You can consider several elastic constants. So you don't have just gradient of Q square. You have this kind of gradients. Yeah. So this is like a divergence. This is summation over repeated indices. So Qij comma j. So this is like divergence of Q squared. This is another kind of mass. And then you have well, this will be still an elliptic to generate an elliptic system. There are repeatable assumptions on the relationship between L1, L2, L3, and you have basically at the level of the equation what you had before, plus this additional mass here. Yeah. And if you try to play the same game as before, you see that, well, it kind of works, but only if you take k is equal to 2. Yeah. If k is not equal to 2, then the whole reduction breaks down. But for k is equal to 2, you still have reduction to a system of 5 ODEs. And you can try to study it before what was happening. So actually, that's nasty. Most of the results are numerical. And what can you have? Well, depends on this additional elastic constant m, that L2 plus L3. And then B again and the radius size. And then you can have 2-component solution, 3-component solution as before, or you can have genuine 5-component solutions. And well, you have things as before, namely components which don't change sign and are monotone. You can draw them and here, yeah. So k equal to 2 really is this x over mod x boundary condition written in terms of matrices. So it's s plus times x over mod x minus 1/3 of j then. Well, you can also have 2-component solutions where you do change sign, something like this, and this is how they appear graphically. And you can have well, 3-component solutions. Okay, this is 3-component, but this is just a line 0. This is just to show that there is a component that changes sign. Yeah. And then as things start getting a bit more interesting, yeah, there is this twist as you approach the origin. And then a full 5-component solution where you change sign, and it's quite a convoluted thing. So, you know, this is still sort of a symmetrical solution, but it's a really complicated one. Okay, and then if you want to do stability, that's a whole diagram of various types of behaviors. So that that theorem that I mentioned in 2020 is just moving something like 1 point years. It's really a lifetime work to do the rest. Okay, 3D. Let me say something about it. Yeah. In 3D, well, you can put again radial boundary conditions x over mod x, and then what can you do? Well, the simplest case is this one. We can allow to reduce the whole system to just 1 ODE. And then you can try to play essentially tricks as before and see the stability. Much less is known about these other two that were initially observed numerically, although again, nowadays we have we have these works that I mentioned to you of Leo, Pisant, and Pasquale, and one hand, and the other side of the world, young demons. Something like this. Okay, so what can we do? Well, so this is the stability diagram, which tells you what happens when you change. This is temperature, so A will move in the opposite direction. And basically this says that as you go with A increasing, yeah, you'll have this as the global minimizer, and then you'll have this ring, more complicated symmetry breaking solution taking place with the global minimizer. This will still stay as a local minimizer for a while, and yeah, and we can try to look at the stability of this hedgehog. By hedgehog, I mean this radial solution. Yeah, and actually, this is work that the four of us, Radu, Valerie, and myself, did here at Hausdorff in 2012, 2011, 2012, and we wasted like 2 months. I tried to prove something which was not true, just because we didn't read this carefully enough. Yeah, so yeah, that was okay. But it was a nice time as well.
Okay, we figured it out at the end. Like we figured out at the end what the problem was.
Okay, so again, this is nice to study because if you make this kind of if you are looking for this kind of symmetry, then you see that in fact it has to be like this. You have this hedgehog, yeah, this x over mod x written in matrix form, which will be multiplied by a function that depends just on one variable. And this generates this ODE. Well, in the whole space, just because we know how we're able to do it in the whole space, doing the same thing in the on bounded domains, it's probably hard unless you do it in a much smarter way. Because it involves a very good understanding at infinity, and for that we do some linearizations of things that are available just in the whole space. And okay, so again, you do the second variation, and then you get this convoluted part, and this is quadratic in B, but then there are these views here that come from the ODE, so you really need to have a very good understanding of that ODE in order to play the trick that I was mentioning before. And in fact, it's nowhere as easy as I presented it. In fact, this was the first paper, and then the previous. But this was humongously technical. Okay, so what can we do? We can show that if you fix B and C, there is some pressure, a zero sum temperature, which such that if A squared is small, so that is to say if the temperature is above a certain level, the most relevant regime, then this hedgehog radially symmetric solution is locally stable in H1, meaning that it happens that the second variation is greater or equal than 0 for all B. And then it was a surprise for us initially, but a posteriori it made sense. This can actually be 0, the second variation, just because you are working in the whole phase. So you have that there are second variations which are, just because of the symmetry, it is a fairly abstract thing that works in general, that if you have a variance with respect to, in this case, translation, then that will make certain variations zero. Yeah. And then if you work for large enough A, you can get instability. Again, instability is much easier. You just produce, a variation that is negative, and that's it. But stability is really convoluted. And
quick question, Arghir. Could you say a little bit about the concept of melting there?
Sorry? Yeah, melting. Well, okay, so let me say what's the melting thing here. So this is what is called a hedgehog. Yeah, it's X over mod X. This has a singularity at zero. Yeah, because at zero, there will be things approaching from different directions. So yeah, you can play a bit and see that it has a singularity. Now, if you multiply it with something like this, you need to put this kind of condition that U of 0 is 0. So this whole thing will become 0 and 0. So that's the melting thing. Yeah. So this is the melting hedgehog, while this is just a hedgehog. And yeah, it's play with animals. Here, but that's the terminology. Okay, so again, you do this decomposition into a special basis, which the basis, now you have R, theta, and phi. So the basis depends on theta and phi. So it respects the spherical symmetry, and you try to reduce everything just to R. It works to some extent, yeah. Mainly, you have that this part of the second variation reduces to something like this, and then you also have some decoupling, yeah, in the component. And well, this is the second variation. You still have couplings, yeah, at the level of theta and at the level of pi, yeah. And then there is the bulk potential, the nonlinearity, where you see this ODE U, yeah, and it comes, in three, say, different packages. And well, what you try to do is to show that this works for any variation, right? So this is the more general variation. Now you cannot really get rid of these terms, so you have to do something about that. You have the pi, which is pi periodic, so that's relatively, I mean, there are tools for dealing with this, so this is just decompose it into the Fourier modes and then see what happens. You, let's say that you manage to get rid of the Fourier modes, you still have this theta variable, this azimuthal angle, yeah, and that is really generating couplings that you have to fight with, and there is a serious fighting because that's not. That's about it. Let me just say that in order to decouple things, you need to create a special basis that takes into account, say, that coupling, and for that you look at you assume that you have the decoupling principal boundaries of R and theta, yeah, because we got rid of the pi variable, and you assume that you have such a decoupling at infinity. And again, is this game that I was mentioning, when you look at infinity, things are a bit better, more linear in some sense. So you look at the game at infinity and you get some eigenvalue problems, you do some formal asymptotics, and you manage to construct at the end of the day a basis that allows you for decoupling. Yeah, so it's getting a really, well, some sort of decoupling. It's getting convoluted, yeah. So that's what, yeah, what happens at the level of basis, and after all this mess, you are left with something that looks as before, namely just depending on R, and then some couplings here. Yeah, you know, had it been for these couplings, you know, life would have been so much easier. But these things are there, and then you have to do these hardy tricks. Say, well, for two of these. Work for a third component, you have to really understand the ODE very well, and also to survive with the couplings. And yeah, and after a lot of pain, you can show that this is zero. So you see, this is pretty nasty already, even just moving around the pole. So let's see what can be done for non-radial solutions. That's or